Hello, my name is Robbin Ehn, and I'm here to talk about handshaking in HotSpot. So I work in the runtime team at Oracle in the Java platform group. This is the famous safe harbor statement. So in the recent years, we have gained a couple of low latency GCs in the OpenJDK hotspot source, and they have exposed some problems with the runtime because the GC used to be so slow that the runtime was never an issue. But now when the GC is actually pretty fast, we have seen some issues in the runtime. And one of the things to solve some of the issues we have done is we have made the handshakes, which is instead of doing a save point, we do a handshake for some of the operations which don't have interthread dependencies. Handshakes are effective but have a limited use case. So since I'm one of the few runtime guys sitting next to the GC gang in Stockholm, I've done some of the work on this. Oh, the clicker. So I will first talk about SafePoint because it's easier to compare. Since we often use handshakes instead of SafePoints, it's easier to understand SafePoints, and also since we had to do a new polling mechanism instead of using the old SafePoint mechanism, it's also good to know to start with SafePoints. Then we look at handshakes, how they're implemented right now, what use cases we have, future use cases, what additional functionality we need for those use cases, and we have some real data comparing a SafePoint to a handshake, so we can see why they are better if they can be used. What is safe? We call it safe when we have no one mutating the virtual machine, meaning your application thread cannot change the state of the virtual machine. To know when it's safe, all mutators or Java thread have states, and we track the states. And there are 4 common states: blocked, in Java, VM, and in native. And they can be easily summarized as unsafe if your application thread is in Java or VM. It's safe if your application thread is in native or blocked. So it's good to remember this picture when we talk about handshakes also. So if your thread are in VM doing class loading or something, we will stop it in the transitions. If your thread are executing your application code, we enable the polls so we can stop them inside Java, or we stop them in the transition when, for example, they go to VM. But we let threads in Java elade to native because native is safe. Native we let them just continue to execute because it's safe. They cannot mutate the virtual machine. And in blocked, we just keep them blocked, simplified. This is how we execute a SafePoint. We have something we call a VM operation. We have a queue, and we have the VMFred, which is the dispatcher of the SafePoint. We put the operation on the queue, and the VMFred picks up from the queue and starts to execute the SafePoint. First, it stops all threads which needs to be stopped, those that are unsafe, and it accounts for all the threads, so it knows which thread it must stop. And when all threads are either safe or are stopped, they become safe when we stop them. So all threads are safe, then we execute the SafePoint, then we restart all the threads. So this is how it can look when you synchronize for the save point. So we have a couple of thread 5 that are going to stop for save point. And here you can see that save point have inter-thread dependencies. So thread D stops early, but it can't do anything. It needs to wait until all threads have stopped. Then we go to save point and it will be started after. So the latency for thread D, for example, can be very long. Also, we have some idle CPU, meaning we are wasting CPU time. And when we restart, it's not possible to start all the thread at once because of OS limitations and stuff like that. We get unutilized CPU on the other side of the save point when restarting also. But there are some upsides with the save point. It's really simple. You start the save point, everything becomes safe. You can do anything you want in the virtual machine. It will be fine, and then you restart. And it's also, compared to handshakes, pretty fast from the requester. So you have the numbers there, and depending on how fast your operation are, if you're using ZGC, you're talking of like a half a milliseconds more until your save point are done. So it's under 1 millisecond. So it's pretty fast from the requester. Yeah, and it's really simple. Either we're in the save point or we're not in the save point. Either we are completely safe or we're not safe. The problems, well, your application will stand still during this time. And we have the problem with the threads are depending on each other. So if one thread is in the scheduler and cannot get CPU time, we cannot start the save point until that thread have gotten some CPU time, hit a poll or a transition, and become safe. And we also have many operations which doesn't have inter-thread dependencies, meaning we're synchronizing all the threads, but when we do the operation, we don't need that dependency. So here is how the old global poll looks like. Is it? So we just test this fixed address. Either it works, or we have set the memory protection, and we end up in the signal handler. So when we're ARM, we flip the global state to synchronizing. We protect the page, and threads hits this. This is when they are in Java code, which is emitted by the JIT compiler. So, and they end up in the signal handler and eventually stops. And in the slow path, where we don't want to hit the signal handler, we can also use this branch poll instead. And when we disarm, we do the opposite. We change the protection to allow reading, and we say not synchronized. So it's simple, the global save point poll. Handshakes. So what are they? They are per thread save points. They're actually a really old comment in the code base which says here we could use thread local save points. It's really, really old. Yeah, so, and handshakes are latency friendly. Why, we will see later. They can be used to access any owned thread resource or owned or local resource for the thread. As example, the stack biased lock or asynchronous exception. So anything that the thread may only access, we can access with the handshake. It's also used often as a barrier because we have a lot of data which is only touched in a while we're touching that data, we do not save point check. So we know if we use a handshake as a barrier, we know that it will either see the updated value or the old value. So after the handshake, it will see the updated value. take a closer look at that also. It is executed the same way as handshakes. We put a VM operation. It's the same basic structure as the SafePoint, but instead it's not a SafePoint operation, so the VMFred will not initiate the synchronization. Instead, we install the handshake operation and we arm that thread polling site, or arm that thread's poll. So all threads that hit the poll will see that it have a handshake operation installed and start processing it. The VMFred will execute the operation for those threads that are already safe. So if you remember the picture I told you to remember, all the green one, the VMFred can execute directly, because all the resources we're talking about belongs to the VM, so it's the Java stack and stuff like that. It's not the native stack.
Or special register assigned per thread poll, or
Oh, it's coming.
Okay.
It's coming. You mean for arming? Yes, the arming is coming. You get the assembler.
Thank you.
So, yeah, as I said, self-processing happens when we hit the JIT poll in a transition. But right now, in the slow path, when we have armed the poll, we need to check if it's a SafePoint or a handshake, because we don't want to emit two different polls in the JIT code, so they share the same new polling site. So in the slow path, we check, was this a SafePoint or is this a handshake? And VMFred just looks at the thread. If it's safe, it can process it. It's handshake for him. It can access those resources. So here we can see the difference between a handshake and a SafePoint. Thread A hits its poll, it does its operation, then it continues to execute. And then it will be context switched by the scheduler. Thread B will get on to the CPU, and sometimes later it will hit his polling site and execute the handshake and then continue. So that's why we can keep the CPU utilization high, and we're not interfering with the latency for the execution of your application. You can obviously measure this in a micro benchmark, but if the operation is tiny, this is not noticeable. And I had that there, unnoticeable. So if you doesn't measure extremely carefully, you can't see the handshakes. We can target individual threads with the handshake. So we don't need to handshake all threads. We can target a single thread for the handshake. And it's really good as a barrier. It doesn't have the thread dependency, and we keep the CPU utilization as high as possible. The problem is, since we only have one poll in the VM, using this new poll causes the arming to be, the arming scales with the number of threads you are, because you need to arm the individual threads. So if you have 1,000 threads, you need to go over all the threads and arm all the one individually, which can be slower than the mProtect. It also causes sometimes complex state, because only that thread and those resources belonging to that thread is safe. The rest of the virtual machine is still unsafe. So sometimes you're kind of want to touch something which is not safe. So if you would take a lock inside a handshake to access common data, things get really complicated. So we try to do simple things in the handshakes. And from a requester perspective, they are slow. They can take, ballpark number is 20 milliseconds. It's because we need to wait for the scheduler to give all the threads their quota. So if you have a slightly over-provisioned your machine, it's up to the OS scheduler until all have gotten some CPU time and gotten to execute the handshake. So, implementation. So we need a unique poll per thread. And the solution we pushed utilized the fact that most architecture have the thread pointed to the thread, which is the Java thread, the native structure for each Java thread in a register already. So it's really fast accessible there. And all the threads have a pointer, and that pointer can be set to either poll or not to poll. And to do that, we have 2 pages instead of one. One that is bad already, one that is good already. So we don't need to do the mprotect. They are already set up from the start. So JIT will do an indirect load to hit the bad page if it's armed, and then end up in the singular handler as we used to do. And in non-JIT code, we do branch-based because we don't want to end up in the singular handler when we are not in JIT code often. So this is for x86. R15 is the register we always keep the pointer to the native structure representing the Java thread. So we have a piece of native memory which represents the thread, and inside there we have a second pointer which points to a bad or a good page. And the poll becomes slightly more complicated since we do an indirect load, so we need to load that. This is R15 if this is x86 64-bit. So we put that address in here and then we test that. Yeah, and here you can see if we were gonna arm everything, we need to loop over every thread we have in the system, which is a Java thread, and arm them individually. So this one will actually call this one, or this one if you do disarm or arm. This is the branching check in the slow path. So I jump to use cases. These are the ones we have right now. There are some future ones which I always will show. So you have the GC ones. So they're not identical, but they are both used for N methods. I'm not sure if Shenandoah also uses this one for metadata or if it's only N methods. Probably some GC guy can answer that if it's only N methods or not. It's both, yeah. So this part they both have, but rendezvous said GC's rendezvous closure is also used for dead week reference resurrection synchronization. And you have most of the ZGC team here, so you can ask them more about this guy. So, but in this case, if we take the N methods, so you ask the code cache for an N method. N method is a compiled method. And while you're handling that N method, we don't do any SafePoint polls. So it can happen that you find an N method which is already dead or dying. By removing it from the code cache, so the code cache cannot give it out anymore, and then do a handshake. After a handshake, no one can have a reference to that N method, and we're safe to free it. And you have another ZGC handshake, which access the per thread mark stacks. Yeah, if ask the GC guys. So yeah, this one is fun. We have the thread stop in Java. That guy tries to install an asynchronous exception on the thread that you're killing. To install that, we have always done a save point. So if you call thread stop, the VM will save point and install that thread def exception on the targeted thread. So since this is one thread talking to another thread, doing a save point is kind of overkill. So now the installation of the asynchronous exception is done with a handshake. But you, yeah. Hopefully we can remove this entirely. So don't use it, even though it's much faster now. Yeah. Revoke one bias. This one is pretty cool. So if a thread have a lock, the first time if you run the VM as normal, the first time you take a lock, what you do is you put in a pointer to yourself on the lock, which says, I own the lock. And while you have the pointer to yourself, you don't need to do anything more. You have the lock forever. No one can take it from you. So, but if another thread comes along and said, oh, I need this lock, then you need to go to a save point because no one can change that pointer because no one knows if that thread is inside a synchronized block or not. So you can't do nothing about it. So you need to ask the thread, can you please turn this biased lock into a basic lock so I can then inflate it to a monitor and then wait on it. And we did this with SafePoints, but we have a lot of heuristics try to avoid this, but it will be a safe point in the end most often.
Are bias locks default now in HotSpot?
Yes, there is an RFR to make them not default and deprecate them, but yeah, but
do you talk about unbiasing due to hash code freezing?
no, it's if I have a bias lock and you want to take it from, or you want to wait on the lock.
No, it's like, so when you want to, like, basically you have to unbias when you take the hash code, right?
Yeah. Anything that causes a revoke, which would have been a save point. So if you want to install the the hash code inside the mark word, I can't remember if it's room in there, but if it's not room in there, if we want to use the mark word for something, we used to need to save point to fix the mark word if that's due to hash code, or if we want to change the thread pointer to a basic lock. So now anything that causes a revoke will be a handshake instead, and that's one-to-one. So I will handshake the one owning the mark word, which I need to change. Deoptimize. This one should have given class some slim startup performance. Since if you do Hello World, I think we do 3 or 4 deoptimizations. So instead of those save points, we do handshakes, which keep the CPU utilization up high. The optimization can happen a lot if you do class loading, class ready defin, if you fiddle with the method handles. Yeah, so we need to walk all the threads in the system, look at their stacks, look if they have end methods, which needs to be deoptimized. Deoptimized means we patch the frame PC for that end method, so we go into the deopt handler instead. And in this case, we have no inter-thread dependencies, so why not just make it a handshake? End method marking closure. This is done by the sweeper thread for those that know internal details of the hotspot. So the sweeper needs to know what end methods are on the stacks of the threads. So we need to walk the stack of all threads and count, or figure out which end methods they have on stack. This also used to be a save point, but we have no inter-thread dependencies, so we can do it with a handshake. future use cases. So we have the suspend flag, which I have a personal hate against. Then we have JVM TI, which uses SafePoint a lot. Yeah. We have monitor deflation, which is the last runtime save point we do now, because we have also spent a lot of time removing save points. So when that's fixed, runtime is not responsible for any of your save points. Only GC and compiler have one. Yeah, the suspend flags are basically per thread. Kind of handshakes, but they're really limited. We only have a certain bits. They're only checked on certain places, so they were not usable. But we still have a lot of functionality which uses them, but we want to remove them and just use handshakes instead. Yeah, you can see those 4, and I think SAP added one more for the when they are doing the local variable reconstitution to be able to run with a JVM TI agent and still read the local variables from the JIT code. So we actually have one more, or if they are pushed or not, I don't know. It's because they were missing some functionality in handshakes to do it with handshakes, unfortunately. JVM TI, many operations are if you target a single thread to do something. We often do a save point. It's not needed. So many of the operations can be a handshake. Yeah, and we can also do this, as several have been requesting this. So when you do stack trace all threads in JVM TI, we go to a save point, take all the stacked traces and give to you. We could do it with a handshake, but there is a different. The stack traces will be taken at different time, so you can actually see the same thread holding the same lock. If you would do that, so it is okay. Then it's no problem. If you do, there is a method which takes an array of threads. If you use that one, it should be in the same save point. Okay. Yeah. Monitor deflation. Here we're back into the mark word. So where the mark word is pointing to an monitor. Monitor is the native structure which you can actually wait on. And we want to change that pointer, but we want to do it in an ABA safe way. And when we are playing with the mark word, we don't have any polling sites, so we can update the mark word, fire a handshake, and when the handshake is finished, everyone will see the updated mark word. G at store load barrier. So the concurrent refinement threads are cleaning cards at the same time as you are dirting in them. So every time you write, you need a store load barrier to make sure when you dirty the card, your next load doesn't pass that dirting of the card. So, and the refinement thread can instead use handshakes to get the store load fence. So they would clean multiple cards and then fire a handshake. Again, GC people in here if you need better details. This is something pretty cool. It's the ZGC stack watermark barrier, which is been worked on right now. And that means that we're trying to do concurrent stack scanning. So instead of accessing the stack inside a handshake or a save point, we're actually accessing the Java stack while the thread is running. But we need a way to stop the thread from accessing the part that we are looking at the same time. So this will require branch-based polling, we think, or we're pretty sure. So we would, every time we return from a method, we would check where in the stack we are. If we try to go under the watermark, we will stop because we have a concurrent GC thread working on that part. This one I know Mikael Jardin loves, doing safe points with handshakes. So in the slow path, we need to check if there is a safe point or a handshake. We could implement safe point with a handshake. So a handshake is just an operation which stops the thread. This simplifies the VM. Wouldn't affect you guys at all, but it's to keep the code in better shape. We have some concern about ordering. Right now, if we would add, I think it's this guy, asynchronous handshakes. Right now we only have synchronous handshake. If we add this one, we need a per thread queue. That means that handshakes and safe point can become, we don't know the order because safe point is outside the queue, and then we have a queue with handshakes. We don't know if the first 3 handshakes should be done before the safe point and the last 3 after the safe point. Having the safe point as a handshake, it would be in the correct order in a queue that's per thread. So we're not sure that we need ordering, but we think so. This one is pretty cool. The direct handshakes. You remember that all the handshakes go through the VMFred with the operation. So when we're revoking bias lock, we have 3 threads involved. The requester that wants to revoke the bias, you have the VMFred executing the handshake, and the target thread that owns the bias. We thought it was working, so it was pushed, but then backed out, which do this Java thread to Java thread. So we never have any VM operation go through the VM thread. So we handshake Java thread to Java thread. Unfortunately, there was no latency improvement. It seems that the VM thread does this pretty fast, so we didn't see that. But if you have 10 threads revoking 10 bias at the same time, it goes as fast as 1, since they are independent of each other. Otherwise, they are serialized through the VM thread and the queue. Yeah, I touched on this one. Asynchronous handshake. So the main function of this is that we have some use cases to have a handshake which we only want the thread to execute. We don't want the VM thread to do it. It's only for the thread. It means it could be sitting there, because if the thread is in native, it can run for days, months before it tries to return to Java. Then it needs to do this handshake.
How does it work today, and since time immemorial, when a native thread, how do you prevent it returning to Java when you're safe?
The arms, the poles are arms.
Right. So we'll hit a safe point to poll immediately.
Yeah, exactly. Yeah. So for example, if you take the suspend case, so I want you to suspend, you're running in native. The suspend request can be there, be forever. Yeah. So yeah, as I said, it's for some of the suspend flag use cases needs this. And then we have the branch-based polling. It's mainly for the concurrent stack scanning, but also a synchronous exception, which may only be delivered at certain times. We cannot always deliver it. So if you would arm the poll, you would, in the slow path, figure out, oh, we can't deliver this, and then you need to roll forward to the next polling site, until we can that. So we would like the polling sites only to be armed for those places where we can deliver the asynchronous exception. There might also be more than this. We're not sure exactly what needs to be done at certain transitions or places and what don't need to. Yeah, so real data. This is a Safepoint with ZGC. And if you can't read, that's okay. All you need to see is the dots. The dots are bad. Your CPU is not doing anything. So we can see for Fred J5, it stops here, it starts here. But the save point is just here. So the latency for your application will be from here to here. And it can be worse, of course, if your thread stopped here and starts down there. And this is after faster save point. So if you're running a release before we did the faster save point, it's much worse. Because without faster save point, we serialize everything over one mutex, which means the VM threads hold some mutex, and every thread in the system needs to pass that mutex before it can start. This is how a handshake looks. As you can see, the time here, 26 milliseconds, and the time here. So it takes forever, but the CPUs are unaffected, except for there's one problem in this picture. It's here. The VM thread actually uses up its entire time slice before leaving the CPU, and J2 can enter and do whatever he does, probably his handshakes also, and then the VM thread comes back. So we're missing back off on the VM thread. So when the VM thread finds that all threads are unsafe, I can't do anything. It keeps spinning. So we're burning a lot of CPU here. So this is a problem we're going to look at soon. The details here, if you want, you can get the slides and read them, what happens. But the main point is the dots. I think I'm done.
Cool.
Or actually, since I have 38 minutes, I added some extra slides yesterday. Or?
Yeah, you have like 10 minutes, 10 to 20 minutes to...
Yeah, sure. I'll do the extra slides. So the VM is really old. So it uses mutex, and for anything that's lock-free, it uses type-stable memory. We're trying to do something better. First, we had a problem with the Java threads. They were a linked list, protected by a mutex. But since you saw, like when we ARM, we need to loop that list. So that mutex was pretty hot because everyone wanted the threads list lock, because then the threads are safe to touch. So what we did was start using hazard pointers instead. So you get a snapshot of an array which you can use for as long as you like, and all the threads on that list are safe. And when you're done, you just throw away that. It will clear your hazard pointers, and the threads that are trying to exit can exit and stuff like that. It's pretty cool. Hash tables. We used fixed size hash tables protected by mutex or spin locks. And also type stable memory. We have some that are like, we never remove anything from them, so they don't need to take a spin lock or a mutex, so they are essentially type stable memory. And we changed that to using concurrent hash tables, using epoch-based reclamation or RCU, which gives us we still have a constant time reads while resizing and stuff like that. So we had an issue with the string table taking a long time inside the save point, and this was one of the things we did to be able to concurrently delete stuff from it outside the save point. Yeah, and we faster save point, I mentioned it. So we had one mutex, which everyone went through. So when you're gonna stop, everyone needed to take the same mutex. So if 10 threads hit the pole site at the same time, all 10 of them will try to take this mutex. So they will be serialized until they can stop. And the same time when they woke up, all the threads needed to take the mutex and release it and then start. So we changed this. We're using a few ticks where available or a cooperative semaphore solution. Yeah.
Cool. Thank you. Questions? There's a huge injection of JVM internals. Thank you very much.
Maybe a question for the GC guys, but I'll ask you anyways. Pause times are somewhat interesting, but can be fairly well managed these days. The bigger problem is the impact on mutator performance. And I'm wondering if any of this work is actually going to translate into seeing less of a hit on mutator performance as we move to more concurrency in the collectors.
The G1 store load barrier removal would be a good thing for the mutators.
See that for ZGC or Shenandoah also, because right now their mutator throughput is, could use some help a little bit.
I think you should ask the people behind you.
So do you have a specific workload in mind when you say that we could use a bit more throughput? Okay, so in terms of throughput, I think what we've identified we need more of is to allow higher allocation rates, because we are currently single generational and want to become generational. That's for ZGC, yes. So otherwise, the overhead we observe for the load barriers themselves is very small, and it's not obvious that the amount of concurrent work amounts to things being significantly slower. There is definitely an overhead, but it's not clear-cut that that is causing us an issue. We've had, for example, optimization where we removed atomics thinking that things will go faster. Well, in fact, it made absolutely no difference, because if you're walking the heap, it's not necessarily the use of atomics flipping states around that is overhead, but the fact that you're touching all of memory, and that's going to have the same cost regardless, pretty much.
Yeah, that part I get.
Okay, I think I'd have to see the specific workloads to know to what extent the fact that we're doing things concurrently is causing increased access times.
Maybe we can take that offline since the coffee break is coming up. Thank you very much, Robbin.
Thank you.